Hello, this is Jeffrey Fox again with the last lesson of the last unit of the physics use case. And this is just using this example to describe the differences between the Bayesian and frequency interpretation of probability, a very well-known subject for many, many years. In fact, this was already well understood when I first started working in these physics areas, whenever it was, 45 years ago. So, when we first started off talking about probability, and we produced these 40,000 different measurements of 25, and we said we had a Gaussian, and its mean was 25, and its error was around 5, we were talking about frequency, because we actually generated, well, this is actually 250, not 25, so it's a mean of 250 and an error of the square root of 250. And then we have this Gaussian, which fits the data quite well. It didn't fit it as well for 25 because 25 is not a big number. So that's fine if we have 40,000 experiments. But unfortunately, with CMS or Atlas, we have 2 experiments. And not even the same experiment. They actually do 2 experiments, not for statistical reasons, but for bias reasons, to make certain that the observations are not an effect of the particular experimental setup. So this, although we can talk about this red curve and Gaussian probabilities and things like that, it's not so relevant because we'll never do lots of different experiments for here 40,000 of at the LHC. We don't have time to do that. But what happens? Well, they did the experiment once, and they didn't actually talk about the frequency, the number of times the experiment would actually detect the Higgs particle. They said CERN scientists believe they have found the Higgs particle. So this is very important. So this, of course, I just found this web page, and why I did, because belief is what probability is all about. At least that's the Bayesian view of probability. Namely, when you do this statistical analysis, you're not really talking about the frequency of the number of times you would have seen what you saw. You're asking whether your belief that there is a Higgs or not a Higgs or a supersymmetric particle or whatever you're looking for, you're talking about your belief. And so we really need to think about belief as well as frequency. Because all that counts is whether or not the Higgs is there, not the number of times, what the chance of us happening to see it in the particular experiment. That's interesting, but somewhat secondary as to whether or not Higgs is there. So we have frequencies, which are functions of parameters. And the very simple parameter is the yes-no parameter. The Higgs boson exists or it doesn't exist. Yes or no. That's a very simple measurement. Or we have, of course, we also study the continuous real number, the mass of the Higgs boson. So in the Bayesian view of probability, the probability represents one's belief in the concept, the Higgs boson exists or not, or one's estimate or belief as to the value of a parameter, such as the Higgs mass. In the frequency view, the parameters are fixed, and given the Higgs boson mass, you can calculate the frequency that other experiments will count a certain number of events. Now, actually, as we'll see, these are essentially the same, mathematically very similar. But conceptually, they're pretty different because the frequency view is pretty artificial and uninteresting, whereas the Bayes view is critical. This is really what I want. I'm trying to actually establish whether or not the Higgs boson exists, and if it does exist, what its parameters are. So we do one experiment, or I say, in fact, 2, but that's 2 for a different reason. But even in that one experiment, we can actually observe the Higgs mass in multiple ways. We can look at its two photon decay, which we did earlier, and this other one here is the 4 lepton decay. And the Bayesian view allows us to take these 2 observations of the Higgs mass in 2 independent, totally independent, because they're different final states. So Remember, each final state in physics is independent because every event is independent. So Bayes allows us to combine information from a single experiment to produce a better value for the Higgs mass. And so the result of all of this is a Higgs mass and a probability that the Higgs mass has a certain range or a certain value. So that's some sort of thing with 2 GeV centered at wherever it is, 126 GeV. So now let's go into a little more detail about how we convert measurements into Bayesian beliefs. So we want to convert a probability of a given experiment to a belief or a probability of the value of a certain parameter, which is either a yes-no parameter or a numerical value, to have a certain value. Underlying this are what we call conditional probabilities, which where we have they're usually represented by this bar. So the probability of E, which is here an experiment with a subject to a hypothesis such that the Higgs exists, that is the conditional probability that E occurs, a particular measurement, given that H is true. So we think about things in terms of sets in this little two-dimensional world, which is sort of abstract. Then here we have a region which E and H both occur. Here we have the E region, which is bigger, of course, than E and H. Uses and as a set notation, and here we have H. So we have the probability of E is the area of this big thing here. Which is, I should say, the probability is the area of E, or of the area of the world. The probability of H is the area of H, this ellipse here, divided by the probability of the world. And then we have E given H, which is the area of E intersect H, which is this thing here, divided by the area of H. And the probability of H given E is the same sort of intersection region, but now divided by the area of E. So if we take H conditional E divided by E conditional H, you will find it's the area of H divided by the area of E, because the area of the world cancels out, which is the probability of H divided by the probability of E. And so this is Bayes' law. It relates conditional probabilities of H given E to E given H. And this is absolutely critical, this thing, because what we're interested in, what frequency model tells us, is the probability of observation, which is E, given that the Higgs particle exists, which is H. So this is what we measure. But what we really want is this, which is the probabilities associated with the Higgs existing or not, or the Higgs mass being a certain value or not, based on our experiments. So this is very important. Bayes' law converts the frequency interpretation of probability into the belief interpretation of probability. So this is looked at again here. We come back with Bayes' law. H is the hypothesis. The Higgs mass is something or other, or the Higgs exists or not. E is the experiment, and of course we can use, we have this relationship here. And we have something important here, P of H. P of E is not very important because we only have a few E's, and this sort of is the same, whatever, it's independent of H, and H is what we care about. We want to know whether or not the H exists. Is that hypothesis true or not? So we don't care about P of E, so we sort of don't bother with that. But we do care about P of H. In this interpretation here, the experiment E takes an existing probability of H, the existing feeling about H, and it multiplies it by this, which is what the frequency interpretation of the probability, and it gives us a new estimate of H given E. And this, actually, this thing here should be an actual bar. I will correct that in the slides that you actually download. So, and this thing here is also a bar. So P of H is sometimes called the a priori value of the probability. And when you're coming in there with a non-biased fashion, you would say P of H, at least for the mass, is pretty uniform. It might have some bounds on it for unreasonability, but at least in some region it's pretty uniform. Then when I measure the two-photon decay of the Higgs, I get an actual, from this formula here, but from the two photons, I would actually get a probability distribution for the mass of the Higgs, which comes from the frequency interpretation, which is this nice Gaussian centered 126 with a width of 2. And then I come down to the 4-photon decay mode, or I take CMS, and then I come along to ATLAS. Then the a priori distribution is no longer constant. It's actually what I know already, and I already know something. So what you end up is, this law allows you to accumulate lots of measurements. And so you accumulate a final distribution of H, a belief of the mass value of the Higgs boson, which is the product of all your methods, which could be CMS, ATLAS, 2-photon in ATLAS, 4-lepton in ATLAS, and so on. And you just multiply these things together, as I mentioned. That's because we start off with P of H constant, so the original P of H is nothing. And then every time we do something, we pick up P of E given H as the belief we have in the mass value of the Higgs boson. So this shows you how we can convert frequency estimates to beliefs, and how we do this in a product fashion. So we take multiple experiments and multiple measurements in one experiment and increase our knowledge about either the existence of the Higgs, and if we observe the Higgs in 2 different decay modes, our belief in the Higgs existing increases. And that's what's expressed here. You multiply, your belief improves as you do more things. So this is all very reasonable, and it's intrinsic to everything we do in this field. So that's the end of physics. Have a great time, and we'll go on to some more complicated things. Actually, in this the next section is 51 different use cases, which actually includes this one use case, so there's 50 extra use cases which we'll study. Thank you very much. This is Jeffrey Fox signing off with the physics section and Unit 4 within that section. Thank you.